Hello everyone, I'm Aastha. I'm a software engineer at Bloomberg, and today I'm going to be presenting on the topic why your async code might be slower and how to fix it. So a little bit about me. I did my bachelor's in computer science and applied mathematics, and then I moved to London and joined Bloomberg. So I work with the research integration team in London on Bloomberg's document search and analysis platform. So let's get started. So let's look at a problem that many developers face when they get started with async I/O. So you have some code, you wrap it in async await, and now you realize that it's actually slower than the non-async version. So what went wrong? So the agenda for today is going to be, we're going to look at the core concepts of async I/O. Then we're going to look at the common mistakes that developers make while using async I/O. And we're going to look at the fixes and best practices. And finally, we're going to look at something that's very important, which is debugging your async code and choosing the right concurrency model, whether to go with async I/O, threads, or processes. So what is async I/O? So as the Python documentation says, async I/O is a library to write concurrent code using async await syntax. And it's used as a foundation for multiple asynchronous Python frameworks. And it is often a perfect fit for I/O-bound tasks and high-level structured network code. Now, starting with the core concepts of async I/O, first we have the event loop. That's the core of every async I/O application. And in Python, you can start an event loop using asyncio.run. And this event loop manages and schedules the execution of asynchronous tasks and callbacks. And it runs in a single thread and handles tasks cooperatively. Then we have coroutines that are asynchronous functions declared with async def syntax. And as you can see in this code example, we have a coroutine fetch data that can be paused and resumed using await. Then we have tasks that wrap coroutines and run them concurrently. And tasks are scheduled on the event loop. So as you can see in this example, we have a coroutine nested that is wrapped using asyncio.createTask. And then we simply wait until it's complete. Then we have futures that represent the eventual result of an asynchronous operation. And futures are low-level awaitable objects, and they're not typically created in application-level code. And they're exposed by libraries and some async I/O APIs. So you'll not typically encounter futures unless you're working with a library or some low-level APIs. So now we looked at what is async I/O and some of the core concepts of async I/O. We're going to look at how to convert a synchronous piece of code to be asynchronous. So on the left, we have a function fetch data that calls time.sleep for 2 seconds. So it simply pauses for 2 seconds. And in the main function, we're calling this fetch data function. So now we convert this piece of code to be asynchronous. So we convert fetch data to be a coroutine using async def, and we replace time.sleep with asyncio.sleep. That we're going to look ahead is the asynchronous alternative. And we've also converted the main function to be asynchronous, and we start an event loop using asyncio.run. So we looked at some of the core concepts and converting a synchronous piece of code to asynchronous. Now we're going to look at some of the common mistakes that you can make while using async code that can actually make your program slower. So the first is sequential execution instead of parallel execution. So using async await doesn't automatically make your code run in parallel. So for example, if you look at this code, we're getting the user notifications, then we're getting the recent activity, and then we're getting the unread messages. And then finally, we return all three of these from the function. So each of these tasks is going to wait for the previous one to complete, for the next one to execute. So the execution time in this case is going to be the sum of execution time of all these three tasks. Now, to make this code run in parallel, you could use asyncio.gather or task group to run your coroutines concurrently. So this is a faster piece of code that uses asyncio.gather. And now all three of these tasks start at the same time, and the execution time is dropped to the max of these three tasks. Now, one thing to note here is that this is only applicable when the tasks are independent. So in this case, all these three tasks were independent of each other. So if one task relies on the result of another, then they must be awaited in order and not in parallel. So now we're going to look at a live demo of comparing sequential versus parallel execution. So in line number 16, we have a sequential function that makes 2 calls to fetch data. And on line number 20, we have a parallel function that uses asyncio.gather to make these fetch data calls. And we're basically benchmarking the running time of these two functions and see the output that we get. So this is the output that we get. On running the sequential version, you can see that process A starts and ends, and then B starts and ends, and it takes a total of 2 seconds. Whereas in the parallel version, A and B start at the same time, and they also end at the same time, and it takes 1 second. So here you saw how gather helped us improve the performance. So we just saw concurrency using asyncio.gather. It allows us to run your coroutines concurrently, and all tasks start together. But there's one issue when using gather, which is silent failures. So it's not very great at error handling, and there's no per task control. So for example, if you look at this code, for n equal to 1, this is going to raise a value error. And this code is also going to fail for n equals to true. So if any task raises an exception, gather will raise an exception and cancel all of the coroutines that are still running. So to manage independent tasks, you could use asyncio.createTask that allows you to handle errors per task, and it also allows you to run tasks in background. But even in createTask, you can notice that we have to await tasks separately. So for a more structured concurrency, you could go with asyncio.taskGroup. This was introduced in Python 3.11. For context, the latest version of Python, that is 3.14, was released a few days ago. So for it's a more modern alternative to asyncio.createTask, and this is basically an asynchronous context manager holding a group of tasks, and tasks can be added to the group using createTask. So as you can see in this code, we are using an asynchronous context manager, and then we are also storing all the tasks. So if you want to obtain the results in the end, you can use the references that we are storing. And when this context manager exits, all tasks are awaited. So we looked at gather, createTask, and taskGroup. Here's a quick comparison that I've prepared. So all three of them allow you to run your task concurrently. But createTask and taskGroup allow for more per task control and error handling. And for more structured concurrency, you should go with taskGroup. But it's not supported for versions less than Python 3.11. The next mistake that we're going to look at is using synchronous libraries in asynchronous code. So using libraries not designed for async code can block the event loop. So as you can look at this example, we are using asyncio.gather, and you would assume that this code runs in parallel because this uses gather, but that's not the case. So it uses the request library that does not support async IO. And this code is still going to run sequentially, taking double the time. Now, an improvement in performance here could be done using a request library that supports async IO. So here we could replace requests with IO HTTP that supports async IO, and as a result, the execution time in this case is reduced to half. So here are some of the other libraries as well that you could replace for the asynchronous alternatives, and one of them is pathlibs, which we are going to look ahead, which could be replaced by IO files. The next mistake is blocking the event loop with CPU-bound operations. So async IO runs all coroutines in a single threaded event loop, and executing CPU-bound operation inside a coroutine can freeze the entire event loop. So as you can see in this image on the right, we have a CPU-bound task that runs for 1 second, and then we have an IO operation. So the response to the client is going to be delayed by 1 second, as the CPU-bound operation is going to freeze the entire event loop. So a fix for this could be to use an executor that allows you to offload this to a separate process or thread. And this can be achieved using the loop.runInExecutor method in Python. So here's a quick example that I've taken from the Python documentation. That's in step 1, it's basically spinning up a default thread. In step 2, it's spinning up a new thread pool, or you could also spin up a custom process pool. So here's a demo of a blocking. On line number 15, we have a blocking operation which calls a CPU-bound task, and then it makes a call to fetch data. And on line number 20, we have a non-blocking version that gets the running loop. And it runs the CPU-bound operation using the loop.runInExecutor method in a separate thread. And then it uses the createTask function to start fetch data at the same time. So we're going to look at the output of this. So here's the output for the blocking version. So you can see we have the CPU-bound task which starts, and the execution then pauses for a bit, and then the CPU-bound task gets done, and that's when we start fetching the URLs. Then we have the non-blocking version, where the CPU-bound task starts, and we're also fetching the URLs at the same time. And while we are fetching the URLs, the CPU-bound task gets done. So this was an improvement in performance. The next mistake that we're going to look at is very similar to the previous one. It's blocking the event loop with non-critical tasks. So mixing long-running asynchronous operations with critical code then can delay important tasks. So as you can see in this code example, we are getting the user's profile, and then we are sending the logs to an external service. And then we return the user profile. So although logging is non-critical, it delays the response to the client. So a fix for this could be to use asyncio.createTask, or you could use the loop.runInExecutor method that we just saw. And this allows logs to be sent asynchronously in background without impacting the response time. The next mistake is creating too many tasks. So creating a large number of coroutines, especially for trivial operations, can flood the event loop. And this can introduce a significant overhead due to context switching and potentially slow down your application. So a fix for this could be to batch smaller operations into fewer larger tasks to reduce scheduling overhead and improve performance. Or you could also use a counting semaphore, and you could use asyncio.semaphore to limit the maximum number of concurrent operations allowed. So you could use a context manager to now work with this shared resource. The next one, which I have also personally encountered, is never awaited coroutines. So this results in the coroutines never being scheduled in the event loop, and the code might look fine, but it fails silently. So the fix for this could be to use linters like flake-it async that help you catch these errors early on. And the most common fix is to await these coroutines. The next one is improper resource management. So since async code often interacts with external resources like files and database connections, improper cleanup of these can lead to resource leaks. So the fix for this is using context managers like async with to manage resources. And this ensures that all the resources are properly cleaned up before shutdown. So we looked at some of the common mistakes while using async IO and some of their fixes. Now something that's very important is debugging your async code. So by default, async IO runs in production mode, but there are several ways to enable the debug mode. One of them is exporting an environment variable using Python development mode, passing debug equals to true when starting an instance of the event loop, or if you have an instance of the event loop, you could set debug on that instance. So these are the type of errors that the debug mode helps us catch. It helps us find non-awaited coroutines, so you'll get a warning like runtime warning, coroutine was never awaited. It helps us catch many non-thread safe async IO APIs if they are called from the wrong thread. Then callbacks that take longer than 100 milliseconds are logged, and you could also update this time to be something lower or higher if you prefer. And the execution time of IO selector is logged if it takes too long to perform an IO operation. So you'll see an error like selector took 1.504 seconds or something similar depending on the execution time. So now we're going to look at a piece of code that has some issues. So here we have an unawaited coroutine on line number 15, and we have a slow task. And we're going to enable the debug mode on line number 18 using debug equals true. And on line number 6, we set up the logging to see async IO debug messages. So we're going to see what is the output that we get. So highlighted in yellow are the errors and warnings. So you see a runtime warning that the coroutine was never awaited, and you also see that the function took too long to run. So we looked at async IO debug mode, but there are also several other tools that can help debugging your async code. One of them is scaling, that is a high-performance CPU and memory profiler for Python. So depending on the time your program is spending on CPU versus memory, you can find out the issues with your code. Then we have IO Monitor that adds monitor and CLI capabilities for async IO applications. We have PDP, the Python debugger, and you can use this using import PDP and set trace. And this allows you to set breakpoints and interactively step through your application. And finally, we have PyStack that prints the stack trace of a running Python process or Python code rump. And this allows you to find blocking piece of code all without stopping your execution. So We looked at, today we looked at the core concepts of async I/O, converting a synchronous piece of code to be asynchronous, and several mistakes that you can make while using async I/O, and how to debug your async code. Now we're going to look at choosing between async I/O threads and processes. So use async I/O for high-volume tasks that spend time waiting, such as handling network requests or reading files. Threads for I/O-bound tasks that may also need shared data access. Threads run in parallel within one program, making them suitable for light processing with some waiting. And as you can see in this image, the threads are sharing the code data and files, and they have an independent register and stack. And in the processes, each process has an independent code data and files. So they're perfect for computation-heavy workloads, and each process runs independently using multiple CPU cores for true parallelism, which makes them great for maximizing performance in intensive tasks. So you could use them for intensive tasks like image processing or some heavy calculation. So here's a quick comparison of these three. So use async I/O for efficiently handling many concurrent I/O tasks, threads for parallel I/O tasks with shared memory, and processes for maximizing performance on CPU-intensive tasks. So the key takeaways from today's talk were batch your coroutines using async I/O.gather or task group. Avoid mixing synchronous and asynchronous code. Keep your async workflows separate and avoid wrapping already synchronous code in async await. Execute blocking code in thread or process pools using executors like group.run in executor. If dealing with a large number of parallel requests, use async I/O.semaphore or similar libraries to throttle concurrent tasks. And use tools for debugging. For example, you could use async I/O debug mode to cache blocking calls and non-awaited coroutines. And you could use several of the other tools that we saw today. Thank you. Feel free to ask any questions. And you can find a link to the slides with this QR code.
Thanks very much, Aastha. We have time for a few questions, if anybody has them.
Raise your hand if you have any questions.
It's not a real question, but I just saw the slides are not shareable. If you could make them shareable, I'd love to send this to my org, because this is really awesome. Thank you so much.
Are you not able to access the link?
I can see it. I just can't. I'm not allowed to share it with more people. But I can
Okay.
if that's a me issue.
Are you able to share the link?
Okay, cool. Thank you. Yeah, it looks like it. Thank you. Perfect.
Thank you.
Hey, this is a really good talk, super informative. With the recent release of Python 3.14, I'm curious, like, the whole community talks about how now you have this non-GIL code and you can now execute things in, I guess, close to parallel, if not truly parallel way. How does that impact what we already know about async I/O, specifically with thread pool and process pool?
I am not sure about that. I also need to read that out.
Great talk, really enjoyed it. I'm curious though, when using threads, how do you handle, what are the best ways you handle exceptions that happen with certain functions that throw threads, and how is that different from task group? How does task group handle, exceptions that are kicked off by a task like downstream and stuff like that?
Is your question more about the thread pool?
Well, I'm curious how task group handles exceptions versus thread pool. How they handle exceptions. If one of the tasks throws an exception, how does it handle it versus thread pool?
I haven't used that, so I'm not sure.
Okay, well, let's thank Aastha again for a wonderful talk and all of our presenters. They did a wonderful job.